Welcome back. There's a couple of problems that I want to particularly focus on this video, and this will be the last and final video on the aromaticity topic. The reason being, they provide a very unique perspective on the concept of aromaticity and in particularly resonance. Okay. So the first one is very straightforward. Does the molecule contain a cyclic ring structure? It does. Does it contain sp2? Now, as I said, sp2, sp3, and sp are only assigned to carbons, okay? So as long as all the carbons in the ring are sp2, you're really good to go. So sp2, 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 and sp2. So that's good. And then, is there a double and single? Again, the double and single only pertains to the carbons in this chain, not to other elements. So double, single, double, so that's work out. And then 4n plus 2. Now, the reason I had this particular example is, in the previous example, I only had nitrogen, which only has one lone pair on the inside. Now with oxygen, you got two lone pairs, one on the inside, one on the outside. The one on the outside does not count, only the one on the inside counts. So you have 2, 2, and 2. So that's 4n plus 2 equals, you have 6 total. You can get it out of using n equals 1. So Huckel's rule is satisfied as well. This is aromatic. This is what I was saying, is a very, very unique compound, right? Now, does the molecule itself contain a cyclic ring structure? Right, it does. Second, does the molecule contains sp2? Now, this particular carbon has a plus. So for now, you don't need to worry about this. Think of that as like an oxygen or nitrogen. So pretend as if that's not going to affect your sp2, okay? So that means you only focus on all carbons that don't have, that has a double bond. So sp2, 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 and sp2. So except for this one carbon, which you pretend it's something else for now, because you have to make that statement just to allow you to understand the concept. So except for that one carbon, all other carbons in the chain has met the sp2. Because I told you, because of the positive charge, for now pretend as if it's a different element, okay? And is there, again, for the double and single, pretend as if it's just another element for now, just for time being, and see if the condition is met. It is met, so double and single is met. And you have 2, 2, 2, so 6 total. So 4n plus 2 equals 6, because n equals 1 will give you that. So Huckel's rule is met as well. It's aromatic. But what's really interesting here is, because it's aromatic and it's got alternate double and single, we can move the positive charge around, giving you resonance structures, unique resonance structures. We could have done it for all of the other ones we've done, but I think I personally like to just do it for this so I can show you the purpose of resonance. So what I'm going to do is move this double bond one at a time. Every time I move a double bond to an adjacent carbons, the positive charge would go to the tail of the double bond. Okay, so I'm going to move this over here. So I'm going to try my best to draw this structure. Okay. The double bond has now come here. So the positive charge has moved to where the tail of the double bond was there. So it is now here. This is the first resonance structure. Resonance is indicated by a double-headed arrow. The rest of the bonds stay where they were. Now you can move this bond one more place. Sorry. One more place. Or you can move this now. You can move You can move this bond here. That means the positive charge would go to the end of this one. Right? This bond stays here, but we move this bond over here, so the positive charge would go to the tail of where the double bond was, and this bond stays here. Now we can move this bond one more time over here. We can continue this forever. The idea here is none of this structure is a true representation of the molecule. They all have a shared responsibility on what is considered. So the double bond, we haven't moved this, we have this here. This bond is now moved here, so the double positive charge would move here. So this is a variety of resonance structure for the same molecule. That in itself is a proof that the molecule is aromatic. The fact that you're able to do this, you can only move the double bond either to the left or right, one adjacent carbon. Okay, you see I didn't move too many things. So we can keep doing this. Eventually we'll end up with where we started, and that in itself means it's aromatic. Okay, this is the last one. Again, does the molecule contains a cyclic ring structure? It does. Does it, again, for now, well, the negative, it's actually very easy. Think, for now, just to pretend as if the negative is just another element. So that means for now, we can say that the sp2, sp2, sp2 is assigned to all the carbons, which makes it planar. And then there's a double and single, again, as far as this is concerned, right? Which makes it, again, which offers you resonance. And then the negative charge, on the other hand, is same as a lone pair inside the ring. Okay, so this is 2, this is 2 and 2. So the negative charge is same as a lone pair inside, so that's 4n plus 2 equals 6. N equals 1 will give you that result. So Huckel's rule is met as well, so it's aromatic. And just like we did for the previous case, we can have multitude of resonance structures for here. We can move the double bond to this place. That means the negative charge would come to the tail of where the double bond was. It's easier to work with the 5-membered versus the 8-membered or 9-membered. So the double bond moved here. This bond stays here. You can only move one at a time. So the negative charge came over here now. Now again, we can move this bond over here, right? And then the negative charge would go there. You can just keep doing this, okay? Keep moving one at a time, okay? Now we've moved this, right? And then, sorry, I just didn't draw it perfect enough, but you kind of get the idea, right? Again, we can move this over, right? And then the double bond would, the negative charge would move further up, right? This stays here, this stayed here. The negative charge basically comes to the tail of it. You can keep doing this. Again, the fact we're able to do this tells you it's aromatic. All right, now here's Sol. Again, this is sp2 and sp2. Does the molecule contains a cyclic ring structure? Yes. Again, we have 2 carbons that where sp2 is not met, so right away we can say it's not anti-aromatic. Okay, so I want you to practice all of this, and I want you to draw resonance structures in addition to determining resonance structures for this molecule and this molecule. I would be carefully examining this as I read through your my thoughts. So I want you to determine whether it's aromatic or not. And for just these 2 molecules that I've indicated, I want you to draw resonance structures like I did for the previous one. All right, it's going to be tough, but give it a shot and I will help you in class. All right, and that's all I had to say about aromaticity. And I'll see you with another topic.